All right, Algebra 2 students. This is Mr. Shack coming right back to you with another review video. This is the Module 3 test review. I'm going to try to get in the habit of making these review videos for you because I feel like it's a good way to have you guys studying, making sure that you're thinking through these correctly. But again, I'm doing this on my prep. I only have a certain amount of time until students arrive for class. So I got to go kind of fast with these. Just a reminder, it's a video, so please, please, please stop it, okay? Don't just, if you're just watching this through without pausing it, you're doing it wrong, okay? Because if you're just watching this through, I'm going way too fast. You're not really thinking about what's going on here. So pause it, think about what's going on, maybe be trying to work through, and then when you get stuck, that's when you go reference the video and you can check your answers and stuff like that. Okay, so don't just be madly copying everything down. That's not preparing you for the test. Okay, so really make sure you're thinking about this stuff. And let's get started right away. I'm going to focus this. It looks a little blurry. Maybe that's a little better. All right. So first, we're talking about the function negative x to the fourth times x plus 3 times x minus 11. And we got to figure out the end behavior of that. Okay, and there's a few ways of thinking about it. One way is we know, okay, x to the fourth, this is like to the first because there's no exponent, and this is to the first also. So total, it's 4 plus 1 plus 1. This is degree 6. It's a degree 6 polynomial, and whenever we have even degree, it's the end behavior is going to go in the same direction, okay? Usually up like that, but we have this negative down here, okay? So this negative down here, and it's not going to be a perfect parabola because there's multiple zeros, so I probably should have drawn it more like something more like that, okay? But either way, going up in the same direction. And because of this negative there, it's going to flip it. So both arrows are going to be going down, and there's going to be stuff going on in the middle, something like weird, okay? But we don't need to know exactly what that is because we're just talking end behavior, okay? So if we think of it this way, then it's, okay, well, because of this negative, that's why it's flipped, remember? And because it's degree 6, it's going to go the same direction whether our x is approaching negative infinity or positive infinity. So we can say, well, as we go left on our x-axis, we're approaching negative infinity, or as we go right on our x-axis, we're also approaching negative infinity. So as x approaches negative infinity, f of x, nope, it's not that one. As x approaches negative infinity, yep, our f of x approaches negative infinity. Now as x approaches positive infinity, as we go right, yeah, once again, our f of x is approaching negative infinity, so that's why it is b. Now, if that whole degree thing is like, and you can't picture that graph, you're thinking that's really confusing, I can never do that. You should be able to, remember, because if it's an even degree, you got to know, okay, well then both arrows are going to go in the same direction, whether it's up or down, and you know they're going down because of this negative out front, okay? But if not, you could always put it into Desmos or a graphing calculator. I'm going to kind of switch off showing Desmos and graphing calculator, but let's go here. And it would just be simply plugging it in. So we have negative x to the fourth, oops, not money sign, to the fourth. And then x plus 3 times x minus 11. So I just enter that in. Not equals 3, x plus 3, sorry. And then times x minus 11. Okay, close that. All right, now, gotta zoom and you gotta probably change the window here. I'm gonna change my y-axis to like negative 1,000, positive 1,000. Okay, gotta know how to change these windows. Come on, what happened here? Oh know why it's not letting me click there. Okay, let's try this again. Oh, you gotta love when it's just not doing what it's supposed to. Okay, here we go. So 1,000. Okay, now we can see that both end behaviors, again, as we go left on our axis, as x approaches negative infinity, our graph approaches negative infinity, and as x approaches positive infinity, our graph again is going down. Okay, so that is number one. I'm going to have to pick up the pace if we're going to get through this whole thing, so I'm going to try to do that. But some of these are just going to take longer to explain. Now, number two, we have an art teacher uses two boxes, okay, to store her art supplies. Awesome. The first box has dimensions x, 3x, and x plus 5, okay? And then the second box has dimensions that are each 2 inches longer than the dimensions of the first box. Okay, so we need to be thinking here. All right, well, how do you find volume of any box? Well, it's each dimension times each other. So x times 3x times x plus 5. That would be volume of the first box, but it wants to know which function models the volume of the second box. And the second box has dimensions that are each 2 inches longer. Okay, so this x is 2 inches longer, so that turns into x plus 2. Our 3x, 2 inches longer, so you got to add 2 there. And now our x plus 5, that's like I'm adding 2 to that. Well, what's 5 plus 2? It's 7, so we get this, x plus 7. Okay, and that ends up being letter C. Okay, maybe I'll zoom out a little bit there so I don't have to keep sliding the paper. Okay, now this question is an interesting one. I'll show you it on the graphing calculator since I used Desmos for the last one, but you can do this on Desmos also. You're entering your equation, so I'm entering x plus 2, 3x plus 2 times x plus 7. So I got x plus 2 3x plus 2 and x plus 7. Okay, I'm going to graph it. We're going to see it come in, and it's just going to look like a lot of lines right now because a lot is going on. Okay, but if the volume of the second box is 2080 cubic inches, I guess we probably should have started there. Well, remember, we said our volume equals this. So x plus 2, okay, again, I'm just copying what we picked for our answer because that's what we're saying our volume is, times x plus 7. Okay, and now it's saying if the volume is 2080. So instead of saying that equals v of x, we're going to replace that v of x, replace our volume with 2080. Okay, and now there's a few ways of doing this. Okay, on the graphing calculator, I have to trace. So I'm going to go to trace. I'm going to try to find, here's my cursor. You see it there, hopefully. Okay, and I want to know when y is equal to 2080, what is my x? That's what I'm trying to figure out here. So I'm going to go up, and it's going to climb rapidly. It's off of my screen, but that's okay because I'm just watching down here to see whenever my y equals 2080. So I just keep on going. I'm going to have to keep going, keep going, keep going. And here, right here, is where we fall. It doesn't get to exactly 2080. That's okay. It's jumping around it at 2014 and 2124. But at 2014, we're at 5.9. And at 2124, we're at 6.06. So I think it's safe to say that at 2080, we're at right about 6. So for my answer here, I can just say, well, my y is going to be 2080 when x equals 6. And I found that just by using my graphing calculator. Okay, if you were to use Desmos, hop over and use that quick. Okay, so we got x plus 2, and I just want to show you this real quick because it's really easy on Desmos. X plus 2, 3x plus 2, and x plus 7. Okay, and now what I can do, if I'm trying to figure out when it equals 2080, watch this. I'm going to say equals 2080. Look at this. And now I can just go ahead and it just gives me the line here. It's going to let me click the line. I think it's because I'm on Screencastify, and I don't know if you can see this because I'm recording my screen. It's not going to exactly show, but I can zoom in and you can see it's right at 6, like we thought. So you just have to enter that equals whatever you're trying to have it equal if you're using Desmos for that. So that's kind of cool. Makes it nice and easy. Let's keep moving here. Number 3. Okay, number 3. We're trying to figure out what equation represents our graph that we have to our right here. Okay, so I'm looking at these and I'm thinking, okay, well, it has to be an odd degree because it's going up in one direction, down in the other, but they're all odd degree, right? Because it's all 3 of them. So now I need to look at my zeros. Okay, and there is a 0 at x equals -3, x equals -1, and x equals +2. Okay, so those are my zeros. And if those are going to be my zeros, I have to think, okay, well then, what's going to give me x equals 2 is x minus 2. Okay, because if I were to solve for x here, like if I set this equal to 0, I would have to add 2, that'll give me x equals 2. Okay, what's going to give me x equals -1? That's x plus 1. And there's a few ways of thinking about it, like the way I just explained with setting it equal to 0, or just thinking of it like it's in the parentheses, so it's the opposite again. Kind of like with h when we're doing our transformations, it's the opposite. So opposite of -3, then that has to be x plus 3. Okay, so now I got the 3, and it doesn't matter what order they are. I'm just looking for the one that has all 3 of these written correctly, and that is D. Okay, so again, I know I'm going fast, but pause, think about it. I hope you are not just trying to write down everything I am as quick as possible. That's not the way you should be watching this video, okay? Moving on to number 4. Okay, we have which statement describes the transformation used to obtain the function x plus 5 to the 4th minus 8. Now this one can go quick because we're just looking at, okay, this is our h, this is our k. It's plus 5, but it's in the parentheses, so we got to think of it, it's like a minus 5 because it's x minus h. H would have to be a -5 if it's going to turn into a plus, so we are going left 5. So it's either thinking of it this way or thinking, okay, it's in the parentheses, so it's opposite of what it looks like. So it's left 5. 5 units to the left. Okay, these are both 5 units to the left, so it's C or D. We can cancel out A and B. It's neither of those. And then this minus 8, it's outside of the parentheses, so it's going to do what it looks like. It's going to go down 8 because remember, K moves it up and down. So 8 units down, 5 units left. That is C. Okay, and remember, what I'm talking about here is the whole A, F, x minus h plus k that we've been talking about since module 1. Okay, so that's how I got that. Again, pause and think about it. Think about why that's the answer. Okay, how many turning points here? When we're talking turning points, okay, I've showed enough on Desmos by now, and I'm running out of time before my class gets here, so you should be able to enter this into your graphing calculator or Desmos. You're going to have to change your window to zoom out, see how many turning points there are. Or you can know, okay, well, what's our degree here? Our degree is, well, it's 2 plus 2 is 4. And then when we don't see an exponent, it's a 1 over here. So our total degree here is 2 plus 2 plus 1. So this is degree 5. And our turning points, it's always going to be 1 less than our degree, actually. So we can say 4 turning points, simply because it has to be 1 less than our degree. Otherwise, go ahead, plug this into Desmos. I'm not going to plug it into Desmos, but I want to show you what I mean when I say change the window. In order to see all the turning points, a lot of times it's going to be way too zoomed in. So you're going to have to change your y value to go to like negative 1,000 to positive 1,000, stuff like that. Or maybe even negative 2,000 to positive 2,000. You're going to have to mess around with these guys, changing them around to make sure you can see all the turning points. And then like here on this graph that I have up, this right here is a turning point, and this right here is a turning point. So it's a turning point is just any time it changes direction. If I were to take the time to plug it all in, we would see that it changes direction 4 times. Otherwise, you can just remember the fact that, okay, degree is all the exponents added together, and when you don't see an exponent, it's because it's just raised to 1, okay? So I added up 2 plus 2 plus 1, that's degree 5. Turning points is always 1 less than the degree. So a few ways of thinking of that one. Okay, now place an x in the table to show whether each statement about the function, here's our function, 4 times x plus 5 to the 5th, is true or false. Okay, the function g of x is a vertical stretch of its parent function. Vertical stretch is always going to be our a value up front, and there is 4 here, so that is true. It is going to be vertically stretched. Okay, now I go on and I think, okay, is this going to be symmetric with respect to the y-axis? Okay, and that means it has to be an even function. In order for it to be an even function, it has to have an even degree, and this doesn't. Okay, and that's just step 1 of finding out if it's symmetric, but it doesn't even have an even degree, so that is false. Plus, this is going to shift it to the left 5, right? So when it's being shifted horizontally, that's not going to make it symmetric with respect to our straight up and down y-axis either. Okay, now the function g of x has a global maximum. Okay, in order for there to be a global maximum, it can't have any end behavior of approaching positive infinity. Is our graph ever going to go up to positive infinity? And again, you see that when there's a degree of 5, it's going to look something like this. It's going to be some crazy stuff going on. Okay, this is just a rough, very, very rough sketch. But whenever it's an odd degree, the end behavior as we go left, it's going to go down to negative infinity. And as we go right, it's going to go up to positive infinity. Unless it was negative, then it would flip this completely. But either way, an odd degree, it's never going to have a global maximum because it's going to go up to positive infinity. So that's false. Okay, and if, again, you should probably pause this, practice putting this into your graphing calculator or Desmos, and you can see all of this stuff when you do that also. So really, Desmos and graphing calculator, it's your best friend. If you get good at using those and changing the windows and stuff, you can really pretty much do amazing on this test just by knowing how to use Desmos or a graphing calculator well and knowing what to look for. So then I have placed an x in the table to show whether the graph crosses or is tangent to the x-axis at the x-intercepts. Okay, so looking at that, tangent to is any time that our exponent is even. When it's even, it's going to bounce right back up to the sky. Okay, so it's going to bounce right back. If it's odd, it's going to go right through, it's going to cross. So these both have even exponents, so it's going to be tangent. Okay, and what that means is it's going to hit the axis and it's going to bounce right back up. Okay, I kind of missed the axis, but that's what I mean there. Okay, now when we have odd, it's going to cross. Okay, because what that looks like is it's going to do something like this. It's going to go, and then it's going to, and it's going to go through it, okay? And again, you could put all these into Desmos or your graphing calculator and see that. Once again, here we have all odd. Remember, these are all like exponents of 1. All odd exponents, so they're all going to cross. And here, they're even again, so it's going to do this type of thing where it hits the axis and bounces back up. So we say tangent 2 there. All right, very last one now. Last one that we have is looking at this function, okay, number 8, and we're going to try to figure out, okay, where is this positive and where is it negative? And then it says to graph the x intervals where the graph of the function is positive. Okay, so a good place to start is, well, this is going to cross the x-axis at x equals 4, x equals -3. Remember, it's just like the opposite of each of these because you're thinking, what's going to make this 0? Well, that's 4. What's going to make this 0? -3. What's going to make this 0? That's a +2. And what's going to make this 0? That is a +5. So I can go and plot all these. So I have x equals 4. I'm going to plot that. X equals -3. Plot that. X equals 2. Plot that. X equals 5. Plot that. So I just plotted all my turning points. That's what I did there. And now I'm having to think, okay, well, what's going on with this graph? And if this is even degree, which it is, right, because these are all have an exponent of 1. If we don't see anything, we just think of it as an exponent of 1. So 1 plus 2, or sorry, 1 plus 1 is 2, plus 1 is 3, plus 1 is 4. So 1 plus 1 plus 1 plus 1, that's 4. So we have an even degree, which means, and there's no negative up front. So I don't care what's going on in between, but I know that it's going to look something like that. Okay? So it's going to start positive. So it's going to be positive this whole way, all the way till we hit our first turning point. Then it's going to be negative, right? Because now it's, we can kind of look at this and think of it like if I had it access through here and if this came down a little lower like that. Okay. Then it's going to, if it hits this turning point, then it's got to be negative. And then it's going to hit this turning point. That means it's back up above the x-axis. So it's positive here. And then it dips back down for a tiny little bit, negative between 4 and 5. And then it ends positive this whole last final way, all the way to positive infinity, like it did over here, how it started. Okay, and you could enter that into Desmos or your graphing calculator. I will go ahead and do that actually so that we can answer part B. We're getting there. We're almost done. Very last one. So entering this into Desmos. I have 3. I'm just entering my original equation at the top. 3 times x minus 4 times x plus 3. Okay, times x minus 2 and x minus 5. Okay, so here we go. It's kind of hard to see everything that's going on here, so I'm going to zoom in a little bit. There we go. That seems to be good. Okay, and here you can see what I was talking about. It goes through at -3. That's where it's positive all the way before -3. Remember, we're reading from left to right. Then we hit -3. We're negative, we're negative, we're negative. We hit +2. Then we're back to positive for this little hump. And then we hit 4. And we're back to negative for this tiny hump back till we hit 5. And then we're up all the way. So you could see that where we're positive and negative answering part A. If you didn't understand how I answered part A, see how easy that is to see in Desmos and think about part A again. Pause the video, think about part A now, looking at this graph. Okay, but we are asked in part B, which statement is correct about the maxima minima of the graph of function f of x? Okay, so we're looking at global max, global min, local max, local min. And the first thing I noticed, this is not going to have a global max because it's approaching positive infinity in both directions. So anytime our graph or our curve is going all the way up to positive infinity, you can't have a global max. Okay? We can have a global min though, and if I zoom out, here it is. We have a global min right down here. Okay, that means the lowest point of the graph. Okay, then we do have a local max because we hit this little hump up here. And then we have another local min here because we're hitting another hump down here. So you're looking at all your turning points. This would be a global min because it's the lowest our graph ever gets. A local max because it's in this area, it's the highest it ever gets. And then a local min because, again, in this area, it's the lowest it ever gets. We can't have a global max because it goes to positive infinity in both directions here. So if you're looking at our options then back on our sheet, the one that makes sense is the graph has one global min, that's what we said, one local min, and one local max. So it has to be C. And again, you just got to be able to recognize those. As long as you can plug it into Desmos or your graphing calculator, you just have to know what you are looking for. And for a lot of these, Desmos is easier than a graphing calculator. And more advanced stuff where you're having to adjust the window like that in a graphing calculator, that type of stuff they will likely show you how to do again in college. So if you're thinking, well, I want to use my graphing calculator because I want to go to college, for the sake of this class, it probably will be just easier to use Desmos for stuff like this. And when you're doing more advanced stuff like adjusting the window, your professors in college should show you and refresh you how to do that. Okay, otherwise, if you really want to know and do it that way, come talk to me. I will always help. Okay, so that is the video for this one, guys. Thank you for watching. I hope that that all was helpful. Please ask questions, make sure you're pausing, and let's go and ace this test. See you guys later.